It's not working. Okay, cool. So great to see you all here, and welcome to everyone who's joining us today to continue our Rocky Worlds discussion series. Just a quick reminder of our metiquette. Can you please use your full name when you're asking questions, and keep and also on your little Zoom names. And can you keep muted throughout the talk? And turn your video on if possible when you're asking questions at the end. So now I'm going to hand over to Takanori Kodama to talk to us about the climates of potentially habitable terrestrial planets. So I'm going to stop sharing, and then you can share your slides.
Okay. You can see my slide, right?
Yeah, we can see your slides and we can hear you.
Great. So, is it okay to start my presentation? Right? Yes. And thank you very much for giving me this opportunity to share my recent activity related to the climate of potential habitable planet. So I'm Takanori Kodama from LC Science Tokyo from Japan. In this presentation, I will provide a theoretical overview of habitable environment of the terrestrial planet, which are expected to be a primary target in the next decade. So first of all, the exoplanet science started from here at 1995, Then thanks to the advance in the observation with ground-based telescope and space telescope mission, we already know the many exoplanets, as you know, and start to understand their diversity gradually, right? And this is kind of figure show that the distribution of distinct exoplanet with orbital period and planetary radius. As you know, we already knew that the exoplanet exhibits remarkable diversity. And of course, as you know, these planets called hot Jupiter because of their closing orbit. And thus these planets called super Earth, sometimes terrestrial planet with relatively small planetary radius, similar to theirs, right? Among them, some exoplanets are expected to be a potentially habitable planet with rich ocean their surface. Here is a kind of example. It's a very famous example of the potential exoplanet system called Trappist 1 system. Thanks to the more, great observation, we already, put some constraint related to their bulk composition and the density with the planetary mass and radius. And we can see these planets locate within the very, Earth-like composition, let's say, rocky planets. As a next generation, we are standing in the era of the characterization. As you know, generalistic already gives us a lot of information about the atmosphere. In next decade, we will see the great telescope to investigate, let's say, habitable worlds and also habitable surface environment. Today, I would like to reveal how much do we understand about habitable planet as a next future primary target. But as you know, the Earth is only one target, a known target, known planet with stable liquid ocean on its surface. Here, I try to put a lot of physical and chemical parameters of the Earth in the same figures. Each these parameters play a very, very important role in defining what is the Earth, what the Earth is. Here is rotation period, and here is orbital period as well. And thanks to the existence of the moon, the obliquity of the Earth is relatively stable. And of course, the Earth has orbit around the sun. And here is the radius and the mass of the Earth, and also here the composition of the atmosphere. Of course, as you know, the Earth has ocean, of course, very teeny amounts of water on the planet, but we see a very wide view of the ocean if we go to the sightseeing sometimes, some point. And also, sometimes we could see the ice sheet around the polar region. This is kind of the Earth. This is kind of our understanding of the Earth. In recent years, it has become increasingly recognized that the Earth's environment is defined by the coupled climate system, which contain the atmosphere, ocean, and continent and ice sheet. Of course, as you know, all atmosphere circulate, and also atmosphere can transport the heat from somewhere to somewhere. And of course, the atmosphere can transport water vapor as well and exchange the water with surface through the evaporation, through the precipitation. Sometimes we could see the rain and snow. And also, the ocean also circulates all of the planet and distribute the heat and interacting with atmosphere by supplying the water vapor through the evaporation. And continent also have the topography, modifying the planetary albedo, as you know. And sometimes continent define the ocean current pathways. It's very important to discuss the heat redistribution thanks to the ocean circulation. And at last, the ice sheet play a major role in planetary albedo. Of course, the ice reflects sunlight a lot, but they also serve an important reservoir of water. So to summarize this kind of information, the Earth's climate and the habitability of the Earth emerge from the interaction among these components. The same perspective is essential for understanding terrestrial exoplanet to discuss the habitability of the exoplanet as well. So next, I would like to briefly summarize how do we understand the habitable environment from the perspective of climate modeling. Initially, we can launch easily. We easily to launch one simulation to see the global average climate. So this kind of one-dimensional radiative convective equilibrium models were used to investigate global average climate of terrestrial planet and to estimate, let's say, classical concept of the habitable zone. And also, one-dimensional energy balance model were also developed to investigate meridional structure of planetary climate, let's say, particularly such as the ice albedo feedback. As a result, the computational resources increased day by day, as you know. So three-dimensional general circulatory model became widely available. So I mean that we can easily run a simulation to investigate climate with 3D model. So we can catch the climate and the habitability studies with 3D DCM. So we are able to capture the three-dimensional spatial non-uniformity of the planetary climate. As a result, our understanding expands beyond the global average climate to three-dimensional nature of the planetary environment. As a next generation, climate modeling is evolving towards coupled atmosphere ocean GCM, OGCM here, which can represent climate system. And then we can touch the next global cloud resolving model, which can explicitly simulate cloud and convection to reveal the role of cloud and water vapor in the planetary climate. So this is kind of history of climate modeling to investigate surface environment and also habitat condition. So first of all, I need to explain the concept of a classical habitable zone. This estimation of the edges of the habitable zone were estimated by the 1D climate model. If the planet has ocean located near the center star, such kind of ocean is not stable because of the imbalance of energy budget. On the other hand, such planets locate far from center star. Surface ocean is covered by ice or sometimes frozen, covered by whole of the planet. So here, to estimate the concept, to estimate classical habitable zone, we usually use 1D vertical RC model to estimate the global average climate. Assuming surface temperature with 1D model, for inner edge of habitable zone is determined by the onset of the random greenhouse state caused by imbalance of the energy budget. On the other hand, the outer edge of the habitable zone is determined by the limit of complete freezing, determined by the maximum greenhouse effect of CO2 in the atmosphere. From this slide, I try to explain more detail related to the edges of habitable zone. As I said, the inner edge of classical habitable zone determined by the onset of random greenhouse state. This is because there is some upper limit of planetary radiation if planetary surface is totally wet. We call a Simpson-Nakajima limit. This is TP profile. This is temperature, this is pressure, estimated by 1D model. So if we change the surface temperature, we could see very, strange shape, followed by saturation vapor pressure curve. So here is this figure shows optical depth. This is temperature, this is optical depth. The temperature at level where the optical depth is equal to 1 does not change, even if the surface temperature bar changed. So the planetary radiation emitted from this level remains the same, implying that upper limit of the outgoing planetary radiation. So I mean that because of this atmospheric temperature profile, follow the saturation vapor curve, we will see the kind of limitation of outgoing planetary radiation. This is kind of definition of inner edge of habitable zone. If the planet, I mean that planet with stable ocean receives very strong stellar radiation above this limit. I mean the Simpson-Nakajima limit, we will see the imbalance of energy budget, leading to the onset of random greenhouse state. On the other hand, the definition of the outer edge of habitable zone is limit of complete freezing. This figure showed relative flux. This is flux from the star, and this is kind of the radiation from the planet. This figure shows the planetary albedo as a function of PCO2 in the atmosphere. This figure shows the definition of the outer edge of a habitable zone. So this is PCO2 in the atmosphere. This is the relative flux. So as you know, CO2 is one major greenhouse gas in the planetary atmosphere. So if we put a lot of CO2, we will see very strong greenhouse effect in the atmosphere. So this line indicates the stellar flux required to avoid global freezing. Assume surface temperature to be 273 Kelvin. So above this line, the planet still alive as a habitable planet. Below this line, a planet will be global freezing state. So thanks to this strong greenhouse effect, we don't need strong greenhouse. We don't need strong stellar radiation to avoid the global freezing. But if we put a lot of CO2 in the atmosphere, we will see strong radiation scattering, leading to the higher planetary albedo. So we will see the kind of local minimum. So this point means that the location of maximum greenhouse effect of PCO2 in the atmosphere. So this point creates the outer edge of habitability. Definition of outer edge of habitability. So to summarize, the classical habitable zone estimated by 1D model, inner edge of habitable zone determined by the runaway greenhouse state, or set of runaway greenhouse state. On the other hand, the outer edge of habitable zone determined by maximum greenhouse effect of PCO, the carbon dioxide in the atmosphere. Most of the habitable planet studies still use this classical concept to discuss the habitability of exoplanet. But 1D model cannot take account, for example, atmospheric circulation and heat transportation, and also clouds and the regional climate variability. So it's time to touch this 3D modeling. This is kind of, introduction of 3D general circulation models. One is dynamics, the other is physics part. Dynamics, we usually take account mass continuity or momentum equations and thermodynamic equations and equation of state and water vapors. And the physics side will usually use the large scale condensation and cumulus convection to discuss the cloud or rain and the precipitation. And of course, we take account related transfer and turbulence as well. So once we touch this 3D modeling to investigate climate of the terrestrial planet, we can catch this kind of complex behavior of the planet, of planetary climate. So I will show the example related to the 3D modeling to investigate the inner edge of habitable zone. So if we launch a simulation with 3D GCM, we will see the distribution of surface temperature like this, assuming the present Earth the solar flux. We can see hot point around tropics and the cold region around pole region. This figure shows the surface temperature. This is latitude, and this is a zonal mean surface temperature in the shown by the solid lines. And also you can see the absorbed stellar radiation and outgoing long wave radiation. As I said, if the planet has a wet surface and a wet atmosphere, there is some limitation of planetary radiation. I put the limitation like this. So if we try to increase the stellar radiation which planet received, the surface temperature above like this. We can see very hot surface temperature all of the planet. This result comes from the case just before runaway greenhouse state of Earth. In this situation, we will see very uniform structure of OLR. It means that planet cannot release the planetary radiation above Simpson manageable limit. Of course, we could see very high zonal mean surface temperature as well. This figure shows the global mean surface temperature as a function of stellar flux. Open circle show the result with 1D model. The filled circle shows the result with 3D AGCM. For 1D model, such simulation cannot survive against a very strong stellar radiation. But if we launch a simulation with 3D AGCM, the planet can survive under the very strong stellar radiation. So 3D AGCM predict higher runaway greenhouse limit, implying it devise the inner edge of habitable zone boundaries. So these panels show the distribution of water vapor. It means that I show the relative humidity in the zonal value, zonal averaged, and this is the altitude. So as you can see, here is the case with the Earth-like situation. This panel shows the case just before the onset of runaway greenhouse state. So one reason why the 3D GCM shows higher runaway greenhouse threshold related to distribution of water vapor. We could see very dry region around the branch of Hadley circulation. So thanks to this dry region, planet can radiate planetary radiation above the Simpson-Nakajima limit. So this is the reason planet can survive under the very strong stellar radiation, leading to pushing, in the edge of habitable zone, far from the center star. And also many studies habitable planet strongly associated with, let's say, Earth-like planet. I mean that planet is covered with ocean globally, let's say. So I put one example here as to show the diversity of habitable planets. I would like to introduce the relationship between the habitable environment and planetary water inventory on the planet surface. So this is kind of summary of planet climate with different amounts of water planet surface. If a planet has a lot of water on the planet surface, we call the planet aquaplanet. So usually, this is kind of this schematic figure shows the case with Earth-like state. Here is equator, here is pole. So we could discuss the zonal mean, their values in these figures. Insolation comes from the central star, and also around the equator region, planet receive very strong insolation like this. But in this state, planetary atmosphere is totally wet. So as I said, such kind of wet atmosphere cannot radiate planetary radiation above the Simpson-Nakajima limit. So this planet can transport heat from equator to pole to get thermal equilibrium, thermal stable state. But in case just before the runaway greenhouse state, that planet cannot radiate planetary radiation above Simpson-Nakajima limit. So if the planet receives the insolation above these values, we will see the imbalance of the energy budget, leading to the onset of runaway greenhouse state. On the other hand, if a planet has very, very small amount of water on the surface, in this case, thanks to the atmospheric circulation, planet water locate only around the pole. So we can see very dry region around the equators. So above this dry region, the atmosphere completely dry. So that dry atmosphere can radiate planetary radiation above the Simpson-Nakajima rim. So that kind of planet called the land planet. And also land planet can maintain liquid water around the polar region, even if planet received installation larger than the onset of a runaway threshold of Akka planet. It means that land planet has wider planetary, wider inner edge of habitable zone. On the other hand, for the outer edge of habitable zone, as you already know, we can see cloud and large area of the sea ice on the planetary surface if we assume the Akka planet. So these elements increase the planetary albedo. On the other hand, land planet has very small amount of water on the planetary surface, and also location of wet region is only around the pole region. So we can see dry surface around the equator and a very small area of ice-covered region, coverage. So it means that planet, decreased planetary albedo. So under the same insolation, land planets were warmer than the ocean planet. I mean that Akka planet. So I tried to run several types of the water distribution with CDCM to investigate the age of habitable zone. This is some summary figures. This is the relative solar flux. This is the random fraction. Random fraction means that the ratio between dry area and the surface area. So zero means that the planet covered with ocean globally. The one is completely dry planet, I mean. So these upper points show that in the edge of a habitable zone with different land fraction, the lower points show that the outer edge of a habitable zone, assuming the complete freezing with different surface distribution of water region. So as I said before, we can see very dry atmosphere if we assume the land planet. Here, this figure shows the relative humidity, total mean relative humidity. So thanks to this dry atmosphere, the planet can radiate planetary radiation above the Simpson-Nakajima limit. I mean that onset of runaway greenhouse of the Akka planet. So this is the reason the inner edge of habitable zone of land planet wider than the Akka planet, one with Akka planet. And also for the outer edge of habitable zone, we can see more, very small area of ice coverage, even if we decrease this insolation about to be 77% of insolation of present sun. So the other planet also has wider habitable zone related to the outer edge of the habitable zone. And also, as you know, due to the difficulty of the planet observation, terrestrial planets around Roman stars became primary targets, as you know. This planet has permanent day side and night side. So the atmospheric circulation is quite different with the circulation pattern of the Earth. So thanks to the hot region and the strong convection, we will see the very thick cloud. And also we can see the overturning circulation from day side to night side. So this figure, compile the climatic behavior with the result estimated by the 1D simulation and also the three-dimensional AGCM. Please see the yellow line and also black lines. This result is come from the simulation with effects of cloud in radiative transfer, and also the yellow line show that kind of simulation without no cloud. So this figure shows the global surface temperature and H2 ratio, the planetary albedo, and also greenhouse effect. As you can see, if we try to take account effects of cloud in global atmosphere, global climate, I mean, for the tidally locked exoplanet, the cloud create very higher planetary albedo, and the planet survive their surface habitable environment against the very strong insulation from the central star. This is kind of, let's say, typical climatic behavior of the tidally locked exoplanet around Roma stars. Thanks to a lot of simulation to investigate climate for the tidally locked planet with 3D AGCM, we understand climatic regime of tidally locked planet with relativity deformation radius and also line length. The relativity deformation radius is kind of a relationship between the gravitational destroying forces and the Coriolis force, leading to the discussion of the horizontal scale of global circulation. I mean the extension from this side to that side. On the other line length is kind of relationship between nonlinear eddies and beta effect, in the Coriolis effect. We can discuss the width of number of zone object. For example, if the relativity deformation radius is larger than 1, global scale data circulation dominate. If the line length larger than 1, less than 1, for example, zonal jet emerged and climate regime became rotation dominated state. This is a typical feature of each climate regime, summarized in the front follows the rapid rotators usually have weak convection with zonal mean circulation, partially connect the day side and night side. And also for slow rotators, they usually have the strong convection activity, and also we can see the thermal direct day-night circulation. And between them, we can see thermally direct day-night circulation and mid-latitude eddy-driven jet, for example. And this shows the climatic behavior where in each climatic regimes, we can see very strong convection here in the slow rotators. And also, we cannot see very strong convection here in the rapid rotators. And also, they show the climatic behavior related to the icy cloud condensate and also humidity distribution of water vapor here. So thanks to this climatic behavior, they also show the typical results related to the thermal flux, I mean this phase curve as a function of phase angle. So thanks to these differences between the climatic regimes, we can discuss the differences, the climatic futures based on the information of observation in the next decade. And also climate simulation have been performed not only the boundary of habitable zone, but also for specific potentially habitable planet, like such as Proxima Centauri B and TRAPPIST-1e. With different background on atmosphere, amount of atmosphere, the atmosphere to change the the structure of redistribution of heat from day side to night side. So we can see the different shape of the open ocean on the planetary surface. And and also recently, we already know that a lot of how to say example to investigate the climate of a potential habitable planet with ADC atmospheric GCM. This kind of intercomparison already began. So they already create a protocol for the type protocol to investigate the climate of TRAPPIST-1e, for example, to see the differences between GCMs. Of course, the most GCMs show the almost same behavior to create a cloud or some concrete result, but we already know the differences between them to translate from the GCM result to the transmission spectra, for example. We can see there were different transit depths related to H2O in the atmosphere from the result of GCMs. So what the last part of my slide is kind of challenges toward habitable worlds. Next challenge is to understand how coupled climate system creates habitable environment on terrestrial planets. So I will introduce the kind of the example with global cloud reservoir model with high performance CPU, high performance computational performance, high computational system. This example is kind of Earth-like simulation with 3.5 kilometer resolution in horizontal axis. This will be show the distribution of principal water vapor and also oil. We could see very tiny structure of cloud and also structure of cloud system as well. So I need to explain why do we need GCRM, Global Cloud Reservoir Model, in exoplanet science. Let's say, first of all, I try to introduce the traditional GCMs. And the traditional GCM, we usually take two parts to estimate the cloud-related behavior. One is large-scale condensation, the other is cumulus convection parameterization. So traditional GCM treat the cloud formation by separating process into those larger or smaller than that grid. So large-scale condensation tells us precipitation in GCM grid scale. And also subgrid scales, cumulus convection parameterization tells us the information of cloud. So traditional GCM tells us the cloud formation and cloud coverage within the GCM grid cell. On the other hand, global cloud reservoir model solve no hydrostatic equation. I mean that no hydrostatic assumption. So it tells us directly simulating cumulus convection and turbulence scaled motions. And also, if we use GCRM, we can resolve the convection and the cloud. In other words, we can investigate the interaction between the convection and the cloud, and also the dynamics, cloud, and the radiation and the cloud interaction, for example. So it's time to run simulation with GCRM as the next step. So we applied the global cloud reservoir model to exoplanet to investigate the potentially habitable exoplanet. To perform, we already performed the simulation with TRAPPIST-1e setting as a case study. For comparison, this is kind of low resolution setup with cloud parameterization here from the CAM or ExoCAM. This is horizontal resolution. Usually, traditional DCM considers 200 kilometers mesh in horizontal scales. In vertical axis, we usually run simulation with 26 layers in vertical axis. And also we assumed hydrostatic assumptions. And here is our settings. We run the simulation with high resolution with cloud microphysics. Our model called NICAM. This is horizontal scale. Our simulation has 10-kilometer mesh in horizontal scale. And also we have 78 layers in verticals. Total grid points around 200 million grids in total. So as I said, we solve the non-hydrostatic Fourier equations, and also we take account to swim Fourier case. And also we take account single moment scheme with 6-type water cloud to mimic the cloud microphysics. This presentation, because of the time slot of my presentation, I totally focus on distribution and also amount of cloud. This panel shows the result from the traditional DCM and also DCM with superparameterization. So we can see red crosses show the substellar point, and this area is day side, and here is night side, as you can see. So as you can see, we can see very thick cloud and very cloudy atmosphere around the substellar point. And also, if we run simulation with superparameterization, we could see the very skinny structure and sometimes the pathway of the atmosphere circulation, for example. So this is kind of high-res resolution global simulation from my team. We confirm the presence of this side cloud distribution consist with those reported by the previous studies. This is day side and this is night side. We can see the very tiny structure of cloud formation along substellar point, and also this cloud transport from day side to night side. So compared to the previous studies, our simulation captured much more detailed cloud distribution and structures. This is kind of next generation challenge of next generation, right? So our simulation shows that clouds are also present at night side, resulting in the planet that is largely covered by cloud, especially for TRAPPIST-1e, if we put the Earth-like environment. As you know, the detection and characterization error tell us a lot of information about the exoplanet. Thanks to DWST, we can discuss the atmospheric composition in the atmosphere, in their atmosphere. And sometimes we can see the summer phase curve to discuss a temperature map and also heat transportation from night side to day side to night side. In the next challenge, I hope we will touch the habitable world observatory. So this great mission will give us the information about the atmospheric composition and also ratio of the ocean, continent, and vegetation, and sometimes biosignatures. And also, if the planet, if this such kind of mission try to watch the potentially habitable planet for a long period, we can discuss time-resolved photometry and spectroscopy. Then we can gradually understand planetary rotation rate and cloud distribution, and also atmospheric dynamics. This is my summary slide. And as you know, the concept of a habitable zone determined by the 1D climate model. Let's say the 1D, one-dimensional, vertically dimensional, radiative convective equilibrium model. But if we try to catch the diversity of the exoplanets, the habitable zone itself, it could be changed thanks to the thanks to the distribution of surface water environment, for example. And next challenge toward habitable worlds is to understand the load of each component. It being that it contains ocean, cloud, continent, and ice sheet as well. So we need to try to tackle on the modeling with the 3D global cloud modeling, global reservoir model, and also AOZ, atmosphere ocean GCM as well. And also just for your information for you, we successfully invite the X-Crime in Japan in next year. So please save date. Thank you very much for listening. I'm happy to take any question.
Thank you very much for that amazing talk. Do we have any questions? So you can raise your hand in the Zoom. We also ask that you turn your camera on when you're asking your question. Do we have any questions? Peter has a question.
Yeah, just a quick one. I really like the way you described the moving habitable zone as a function of the land and ocean, and also the meridional transport as well. I was wondering how important is topography in the land portion? So like the presence of
Oh,
mountains and things like that
mm.
in that distribution of the habitable zone.
Thank you very much for a great point. So for the topography, it's super important to determine the habitability of the planet, for example, in general, to determine the surface distribution of water, liquid water on the planet surface. As you know, the area of liquid water, I mean the ocean, is kind of main source of the water vapor leading to the wet atmosphere. So definition of inner edge of habitable zone is determined by the, limit of the planetary radiation, as I said. So it's super related to with the atmospheric to water vapor distribution. So topography could change the distribution of water vapor. So if we try to investigate the topography of the planet, it's super important to discuss the inner edge of habitable zone.
Okay, we also have a question from Thomas Wilson.
Hi, yeah, thanks for the very interesting talk. It's kind of related to Peter's question, actually, but more going along the lines of the last part of your talk when you were introducing and discussing your climate models. What I'd be interested in knowing is for these climate models that you were discussing, how much of an impact does the surface underneath it play in your modeling, right? Early on in your talk, you mentioned aquaplanets and land planets. So if you couple these ideas together, how much could we learn from our dream HWO observations about the surface of these worlds under their cloud decks?
Thanks for the comment and that's a question. Very great question, I think. First of all, we can touch the distribution of water vapor first, even if the habitable world holds up to the era. So probably we can discuss the amount of water vapor to recognize the how much planet water inventory has, for example. So the amount of water is kind of hide information from the observation point of view. So, but it reacts the global climate a lot.
Yeah, but maybe it's too much to say. Sorry, go on, please.
Please go ahead.
I was going to say, but it would be too much to say about continent distribution on a fictitious planet, to say if there's land here and water here or vice versa.
Okay, so if we will be able to understand the distribution, the continent, and also climate system itself.
Yes, exactly.
We will move to the next step to understand what is habitable planet. Immediately, we can discuss the location of the Earth among the habitable planets. Then we can reflect that knowledge from the exoplanet to the Earth.
Sounds great. Sounds good. Yeah.
Hey, do we have any more questions? We have one from I'm sorry, could you say your name? I'm not sure how to pronounce that. Ruzizan?
Hi, sorry. Can you hear me?
Yes.
I'm
we can hear
Rachel
you.
at university. Thank you for your exciting talk about the wonderful models. And yes, I have a small question regarding the cloud resolved model. I wonder if the resolved model, how the resolved model can affect the predicted boundary of the habitable zone.
Good question. Actually, the habitable zone is super related with the relationship between cloud dynamics and radiation, as you know, right?
Yeah.
So once we run the simulation with cloud resolving model, we can catch that kind of relationship to shape more detail, to shape the habitable planet itself in more carefully.
Okay, thank you so much.
And also, for your information, once we understand climatic behavior with 3D cloud regime model to investigate global climate of terrestrial planet, for example, exoplanet, we can start to discuss with meteorology of the exoplanet. Let's say the cloud self-organization and also tropics behavior of like the Earth. To understand more clearly what the Earth is, as I said.
Okay, thank you.
Thank you very much.
Yeah, better cloud model will have better. Yeah, thank you.
Okay, we have another question from Dennis Sergiev. Good.
Yeah, thanks, Sophia. And thanks, Takanori, for a great talk. And yeah, convection resolving models rule. I actually have a question about land versus aquaplanet simulations and their runaway greenhouse limits. So maybe I missed it, but when you said that land planets tend to be warmer than the ocean, sort of aquaplanets or ocean-dominated planets, is that true for fast-rotating planets and also for tidally log planets, or are there any differences? Because I'm asking because, you know, in the TIE intercomparison, what we saw is that our dry land planets were much colder, actually, and I'm guessing that's because there wasn't just as much water vapor in the atmosphere acting as a greenhouse gas. So I guess this distinction on this slide is a sort of yeah. I mean, I'll let you explain this if you can.
For the tidal rock project, it's very, very important to understand the distribution of water vapor, as you know. So even if the tidal rock planet, if we assume the land planet, and so this kind of dry atmosphere can radiate planetary radiation above the Simpson-Lagrange limit caused by the dry atmosphere. So probably let's say we need to run the simulation a bit, but this is kind of there is some I think there will be the race between the cloud and the effect of dry atmosphere to radiate very strong bright radiation. Of course, the thick cloud lead very higher planet albedo to planet to make cooler. But land planet also radiate strong bright radiation to create the stable, energy balance. So probably there is a race if we consider the tidally rocked land planet. At the outer edge of habitable zone, the problem is transportation of water vapor from this side to that side to be to form the ice cap on the night side, as a discussion with Jeremy before. So it still will depend on the amount of water on the planet surface, I think.
Okay, thank you.
Thanks a lot.
Have we got any final questions? If not, I might use my chair's privilege to ask the last one. So I'm an observational astronomer, and what I was kind of wondering is what would be the thing that we could measure on an exoplanet that would help you the most with models? So you mentioned TRAPPIST-1e. Would measuring the cloud coverage fraction on the day side be very helpful, or is there something else that you'd really like to know about these planets that would help you with making these models?
Okay, I want to catch all of the information of the distribution of water vapor, for example. But terminator is fine, I think. If the amount of water vapor around the terminator region is super related with distribution of surface environment. I mean the surface water vapor, surface water distribution. So if we catch this kind of behavior, information of water vapor around terminator region from the observation information, we can discuss the more lower environment to touch the surface environment, for example.
Okay, I think we can measure water on the terminator, so that's good to know.
Yeah.
Okay, so if there are no more last short questions, then I would like to thank our speaker again for their amazing talk. Next month, we will have Sarah Bruckheimer, who will be talking about her research. Peter, do you remember the date for the next talk?
Not off the top of my head, but it'll be the first Thursday, I think, right?
I think
yes, it should be the first
of September.
Cool. There'll be
I'm hosting it, so I should. Yeah, it's the 3rd.
Okay, so the next talk will be on the 3rd of September, and it will be by Sarah Bruckheimer. So thank you all again, and see you in a month.